There it is. Okay, thanks a lot for the help. Hi, so I'm here to talk about VerMCTS, which, as the slides are showing, is an approach to synthesizing programs for multi-step problems using a verifier, an LLM, and a tree search. These are all my co-authors, most notably David Brandfonbrener and Amin from Harvard. I'm going to start by talking a little bit about the setup. What are we actually trying to do? Then I'll introduce our algorithm, show you some experimental results, and go into discussion. All right, first the setup. As we've heard very often today, here's the kind of basic pitch for this kind of arrangement. An LLM is pretty good at generating code, but it's sometimes unreliable, by which I mean it's probabilistic. It could output anything from some kind of brilliant proof to something that's really not very smart. Formal verifiers, on the other hand, are reliably correct, barring any bugs, but they can't generate programs. So why don't we just combine the two? Why don't we have some kind of mechanism where an LLM is wrapped into a formal verifier? The LLM just can keep generating stuff, and we'll use the formal verifier to kind of sift through the stuff the LLM has generated, checking which parts of that are good and which parts of that are not. That way, we kind of are reaching a best of both worlds scenario, where we've got the creativity of an LLM and at the same time the reliability of a formal verifier. For that, we need a language. Dafny and Coq come to mind. Our idea is here pretty basic. We give the model an English language prompt. You'll see one on the next slide. And then we have it generate specifications, code, and proofs of correctness. So in practice, this often looks like, hey, in Dafny, generate this data, write this data structure. And then write a function that works on this data structure. And then prove some relatively simple proposition about this arrangement. Here's an example. This is very simple, very, very simple problem. The sort of thing that you would see in like the very first week or maybe 2 weeks of an undergrad class on program proving. The problem is write a function repeat that takes an integer x and a natural number n as inputs and returns a list of length n in which every element is x. And then write the obvious lemma about this. We started out just kind of feeding this into the model. And it's worked well for a while. We're kind of monitoring everything. But of course, the question comes up, can we actually trust that the model will output correct specification? Right, is right here, we're starting out with something in the natural language. So we don't actually verify like end-to-end from the prompt into the verifier. And it turns out, and we're kind of trusting on the model to translate the specification according to which the code will be judged. Again, this worked well for a while, but at some point the model started doing things like this. When it found out, hey, looks like actually our like the code we were enforcing for the sorting works really well, even on an empty list, because the only theorem here that we were checking for was like, the output of the function sort is always sorted. And this smiley face is real. This was actually in the model output. This will haunt me in my dreams. I feel like this was the obligatory AI safety discussion here at this workshop. So the kind of solution we came up with for this is we internally have more than just the word prompt. We also have a set of these functions. We call them final check lemmas. These are not visible to the model, but they're kind of just ways for us to communicate with the verifier and saying, hey, we expect this lemma here, repeat correct, to exist and to have exactly this shape, right? And then we inject this whenever we call the verifier without showing it to the model, and the verifier is going to break if the model has not fulfilled its promise to actually create this lemma. Okay. Informally, let me give you a vague idea before we get into the theory. The idea is we start out, we have the LLM generate. The same way that if you just put this prompt into ChatGPT, and then you'll find out if you do this, if you put word prompts of verifier problems into ChatGPT, so you find out sometimes it will work, sometimes it won't. And if it doesn't, you could just press regenerate and try again, right? That's the kind of naive approach here. And our idea is, hey, why don't we kind of interrupt the model every now and then? We generate a little bit, and then from that generation, we check with the verifier, hey, is this code actually correct so far? If it is, fine, we keep generating. If it isn't, then we have to backtrack a little bit. Okay, and we're formalizing this here by saying, hey, we have states, and the state is some kind of string, the prompt and a partial solution. Then we have actions, which are units of a program. That could be each line, if the line does something that's actually self-contained. Of course, if the line is just part of a function, that would be the whole function. In Coq, it would most likely be a command ending with a dot. And then through our dynamics is we concatenate these. And we have a reward function. So the reward function is defined by the verifier, obviously. We have reward 1. That's an accepted complete program, i.e. the prompt is done. We can stop generating. We have, 1 means it's OK so far. We have -1. That's for a rejected program. And 0 for an incomplete program. Now you might be wondering, hey, Dafny doesn't really tell me whether my program's incomplete. We have heuristics here that kind of are able to tell that are supposed to discern between just something that's incomplete, as in, for example, there's a missing brace or something, versus something that's actually already flawed. And from this, we then run this Monte Carlo Tree Search, essentially slightly modified Monte Carlo Tree Search, where we start out with a root that contains the prompt, and we select a branch to evaluate and expand. This, by the way, is the fact that we evaluate and maybe expand is our main change to MCTS. We keep creating new nodes. And then from there, we kind of have a ranking system where each of the nodes gets a value, and we backpropagate our results from running so that we always know where to backtrack if we have to. OK, again, here's how we use the verifier. +1 is verified but maybe incomplete. 0 is I can't verify this yet. For example, there's an incomplete function somewhere. -1 is verified and has failed. And this also, by the way, we're not really distinguishing here between verifier errors and compiler errors. It could be either of those. From that we build an algorithm where we have some prefix, feed that into the LLM, try to expand it, feed this into a verifier, and then check, is this complete? Well, if it passes, we check, is it complete? If yes, we stop. If no, we add it to the tree, give it a high score. If it doesn't verify, then we can either go back to the LLM and say, hey, generate more stuff. This is incomplete. This would be this non-scorable situation here. Or we say, no, this is failed. Don't add, score -1. OK, let's show you some results. These results are using FinCode Llama v2. We're just using one model here, keeping it simple. We have 15 problems that are all hand-designed. This mainly because, of course, the algorithm I've shown you works best when you actually have stuff that requires multiple steps. And there isn't very much in the way of workshops out there for problems of this kind. And then we evaluate based on passity. Passity means the probability that it passes, that we generate a program given a budget of T tokens. Again, if we just asked, hey, can the model generate this? Theoretically speaking, in infinite, using infinitely many tokens, we kind of have a problem of probabilities here, because the model can just try it on indefinitely, and it will most likely solve every problem, if the problem is solvable, of course. So we have a token budget. We have 3 baselines. The first is whole sampling. That's relatively similar to that intuitive approach I was just talking about for you using ChatGPT and just pressing regenerate until it works. We use a kind of more classic MCTS with rollouts. And then finally, we have reflection, which has the model print something and then feeds the verify feedback back into the model, asking the model to self-correct. Here's the results. This is for the problem I've shown you earlier. You see that our stuff is, let's start with the Dafny here. You see that our stuff succeeds at relatively high token budgets here, 5,000 tokens, with about a probability of 0.5. So about half the time it was able to generate a problem, to generate a program and prove its correctness. You also see that for Coq, the numbers are overall much lower, which kind of brings me to the discussion. Since this is the Dafny workshop, what is happening here between Dafny and Coq? Our presumption is Dafny's semi-automation might make proving a little easier for the model. So all the comforts that Dafny has introduced for human programmers are also working well on the model. We not only have the data I've just shown you, but actually there's also several test cases e.g. a BST, which the model actually is pretty much enabled to solve in Coq, but it solves them relatively consistently in Dafny. We think this is most likely due to a bunch of reasons. First, I mean, there's just fewer tokens to generate, and fewer tokens means there's less of a chance to mess up, right? There's also more familiar syntax, which means, I mean, the models that we're using have not been, they're not like specialized necessarily on Dafny or Coq. So, you know, the fact that Dafny uses a syntax that's more close to other languages might help the model. And of course, our mechanics is the model tries the proof once. It might get to try it again. If it still doesn't work, we'll backtrack actually even further. So in Dafny, this heuristic seems to be right in many cases, because you know, if your proof isn't simple, it's likely that your code is wrong. This is not the case in Coq. In Coq, it's often the case that just the proof is too hard, and so we will needlessly backtrack and backtrack and backtrack, leading to this poor performance. Okay, that all being said, what have we seen today? Formal verifiers can act as can operate as drop-in value functions to guide search. We think there's a lot more work to be done. A lot of it is based on, a lot of it is like for the data collection that we're using, we'd like to have more and harder problems. We'd like to have better models here. Also models that are actually like more specifically trained on verification. We'd like to improve efficiency of our measurements. We'd like to actually have learning here. You know, what if a model were to learn how to use, how to write Dafny? And we think that, you know, for that advantage that I just showed on the slide before, there's actually a lot that can be done as well. You know, how do we improve Dafny's semi-automation further for it to kind of match up with the model's intuition more, and let verification kind of guide the development of a proof by an LLM? Thank you so much.
So when it comes to benchmarking, there's a number of Dafny benchmarks out there.
Mm-hmm.
You might think that if you have a system for doing multi-step development, it should do well on these presumably easier single-step ones. So did you try even informally on these other benchmarks?
We've tried very informally, yes. I would say based on that and also based on my intuition, it will work. But probably the distance between our method and whole sampling, for example, would be much lower, right? Because the idea here is for us, we are like whole sampling in that we keep regenerating things, but we try to be smarter about what we regenerate. And if there's only one code unit in the whole problem, then basically we're just doing the same thing as whole sampling, right? So there's, at that point, very little benefit to doing this.
And are all of your changes sort of monotonically increasing, or do you ever like delete or change earlier code? Well,
we backtrack if things don't work out at all. But it's never like we just change one piece. We would completely backtrack, just remove everything, and then explore the branch anew.
In your Dafny Coq comparison, you were looking at passive T, so you're basically considering the budget of the LLM. But I'm curious. There's also the budget of the computation that Dafny and the backend that it's using would be spending, and I'm guessing that Coq is much, it can give both failures and successes much quicker than Dafny because it's not running an SMT solver with all this stuff.
Mm-hmm.
So, like, if you control for that, does this gap narrow, or like what happens? I don't know. Have you looked at that?
Yeah, we have. We've looked at this mainly in the sense of measuring how much time is actually spent in the model versus the verifier. And and luckily for us, maybe somewhat demotivating for those who are working on optimizing these compilers, it's actually negligible, the time spent within Dafny or Coq. It's like I don't have the right number here, but I would informally tell you it's something like 1% of the time being spent on there.
Hi, my question is more about the setup of the problem. Mm-hmm. So you basically give the English description and you're expecting the LLM to come up with the code and the spec, right? Mm-hmm. So how do you confirm that both the code and the spec are meeting the English description? So for example, if you say that sort an array in ascending order and both the code and the specification generated corresponds to the descending order, mm-hmm. which is, it verifies, but it's not meeting what the English description says. So how do you evaluate the correctness in this case?
Yeah, great question. That's what we have this for. So these are the check lemmas. Those are not visible to the model at all. The model always sees only the English prompt and the code it's already written. But those are injected after the code that the model has written whenever we call into Dafny. Where the idea is, so this is a little hard to read, but the idea here is the model is supposed to write a lemma repeat correct. This is in the prompt. And we define a lemma called check repeat correct, which does nothing but just call repeat correct. So if repeat correct did not exist or did not do what it claims to do, then this would likely cause a compiler error or a verifier error.
So kind of in relation to Brian's question about the other benchmarks that were used with whole program synthesis, do you have some comparison of like, are your benchmarks longer in terms of lines of code, or do they contain multiple functions, or how can you actually say even, like, can you see the effect of this multi-step to say, oh, prior approaches, they only synthesize roughly 10, 20 line programs with a single procedure, and we can go up to 100 lines with 5 procedures, or where is it at?
Yeah, I would say that the main difference is really that our tests are kind of covering a different scenario. It's one where we let the model work a little bit like a human programmer would, who has an IDE and who is finding one step after another. The benchmarks, most of the benchmarks I've seen actually are more kind of the sort, complete this one function, right? Where often actually there won't even be an English prompt. It will just be the beginning of a function. The whole thing ends at the curly brace, and then it's asking the model to write at the end of the function. Our stuff, I guess, is able to check whether the model is able to do all of these steps itself, from specification writing up to this. I don't really have a good intuition about the possible length of things. I can tell you that we have, I think the most complicated example we've had were like more complicated sorting algorithms, which are, I think, including proofs, something like 100 lines.
Hi, thank you for the talk. So you gave some intuitive explanation into why it could solve lesser number of Coq problems than the Dafny problem. Is there a similar explanation as to why some of the Dafny problems weren't solved? Meaning, is there some easier program in the benchmark that it could not solve?
Yeah, I think this is kind of a continuation of the general problem with AI, or with LLMs in particular, which is that it's sometimes unintuitive which things it can do versus which things it cannot do. I would say broadly, more complex problems are less likely to be solved, right? But there's so many factors, especially when you're looking at problems that are relatively simple, like the ones we're using, including things like, has this been in the training material, that it's hard to tell.
So maybe there is an explanation that all the problems that it can solve are actually very easy, and it's not really a big deal to solve those problems at all. So have you looked at some qualitative analysis of what kind of problems it can and versus cannot solve?
I think the only answer I can give to that is we are trying, or we've tried to compile a pool of problems that's relatively, that has all kinds of complexities. And in general, I mean, the only real heuristic that I have to figure out whether a problem is hard or not is kind of thinking about which week would an undergraduate student have to be in of some problem proving class to solve this. And I would say there's no correlation there. The model is especially, I think, okay, here's maybe one weakness of the model, and also of this approach, is that very often you've got things like relatively simple problems, and then you build on top of those. So you add extra constraints, for example. These are simple for humans, because we can kind of abstract away there and we can be like, okay, this is actually a two-step problem. You're not two-step in the sense that there's one function then another function, but two-step in the sense that I modify the existing code to add this extra constraint. The model tends to perform relatively poorly at those. I assume it's because it has to keep too many things at the same time in its context. There is, and then whereas in problems that kind of would seem hard, like again, kind of more complex sorting algorithms, I would say are pretty hard to prove, especially compared to the simple stuff here. The model is actually pretty good.
All right. I think we need to move on. Let's thank Simon again.
Thank you.